Hi, in this video we are going to talk about hash tables. So let's get started. So far we have seen binary search trees. We've seen why is it important to make sure that they are balanced, so we are familiar with balanced binary search trees, and we can achieve logarithmic time complexity for several operations including searching, deletion, retrieval, whatever. And the question is, can we do better? And the answer may be quite counterintuitive, because yeah, we can do better. Maybe we can reach the constant time complexity, which is very fast. And this is why hash tables came to be. So we know that, for example, arrays, if we know the current indices, the insertion and retrieval operations are very fast. We can do it in complex time complexity, and this is exactly what we are after. So if we can construct a relationship with the keys and the slots of the arrays, we can make sure that our hash tables and all of the operations with our hash tables are very fast. So here we want to search for a given item with a given key. So we have key value pairs, we have keys, and we have slots in a set of buckets, and we want to find a relationship between the two of them. So we just want to insert, for example, a value that has a certain key. So we have keys. For example, it can be integers, it can be a custom object, it could be strings, such as here, for example, name of famous authors and writers, André Marlowe, Herbert Spencer, Albert Camus. And we want to find the indices in our array. We have buckets with index 0, then index 1, then 2, then n-2, n-1. So we have m number of buckets. So the m denotes the size of the array. And the problem is that the keys are not always non-negative integers, such as here in our example. These are names, so strings, André Marlowe, Herbert Spencer, and Albert Camus. These are not integers, these are strings. So we have to do a pre-hashing in order to map string keys to indices of an array. And we have the key space, we have the buckets, so our array, and we have, for example, several keys, the K1, the K2, the K3, these are the keys, and we try to find for each of these keys a given index and a given slot in our array. Yeah, so that's the main point of hashing and hash tables. So how can we map a certain key to a slot in our array? We can construct the agex hash function, and this hash function is needed. The hashing is that we can map a certain key of any type. It's very important that of any type, not that for integers, but for strings, for given objects, for an email, certain email address, whatever. And we can map a certain key of any type to a random array index in our buckets or array list, whatever. And sometimes they may be collisions. A collision is when we map two keys to the same bucket. So yes, how can we avoid it? There are two solutions for this collision problem. In order to resolve collision, we should use chaining. Chaining is when we store both values at the same bucket, and we use linked list. So we solve this problem with the help of a linked list. For example, our hash function is going to map the key 1 to the index 0, and we insert our value of the key 1 key to here. Then for the key 2, with the help of the hash function, we come to the conclusion then we should insert it at the index n-2, and we insert the value of the k2. Then we calculate the index for the k3 key, and it is a collision. We get the index again, the m-2 index, and we try to insert two items to the same bucket. It's not a problem. We solve this problem with the help of chaining. We store a reference from this bucket of from this slot, this array slot. We store a reference, and it's pointing to the next value, the value k3. And of course, if our hash function is not good, there may be time when we hash each of our keys to the same slot. and then we end up with a linked list. And that's why or worst case scenario is the linear time complexity when we hash each of our keys to the same slot. So the order 1 complex time complexity is of course worse. I mean, we are not able to make it possible because our hash function is not always perfect. And if our hash function is not perfect, it means that the algorithm is not going to be order 1 constant time complexity. For example, here in this situation, if we create linked list, it is going to be linear. The second solution for the collision is the so-called open addressing. We generate a new index for the given item. So we map k1 to the index 0. We map k2 to the index m-3. And we map the k3 to the same place. Then what do? Open addressing suggests us that we should generate a new index. We can increment the index by 1. This is the linear probing open addressing. We just shift our index, and because m-3 wasn't empty, we come to the conclusion that maybe the array index m-2 is empty, and in this situation it is empty, so it is a good solution. So this is the open addressing. So this hash function is very important because it distributes the keys uniformly into the buckets or the array slots. We have the n, and n denotes the number of keys, and the m denotes the number of buckets or the size of our array. A good hash function is the modulo operator n%m, and it is going to give us the right answer if we have integers as keys. And we should use prime numbers both for the size of the array and in our hash function to make sure the distribution will be uniform. For example, the concrete Java implementation of HashMap or in Python, they use lots of prime numbers. And I think in Java, for example, you can override or you can generate the hash function for any of your class, and you see that there are lots of prime numbers there. So it's a very common programming practice to implement hash tables or hash maps in the same manner. If you have string keys, of course, we are not able to use our modulo operator on strings or characters. Then we could calculate the ASCII value for each character, add them up, and make the modulo operator on them. So this is a basic, it is a common programming practice. If we want to calculate, for example, or if you want to assign a number to a given character, we should use its ASCII number. I think the A, for example, the lowercase a is the 61, the 62 is the B, I think, I'm not sure, but something like this. So just to summarize again, Hashtable is a data structure used to implement an associative array, as we call it, a structure that can map keys to values. So we have key-value pairs. It's important that in a binary search tree, we just have values we want to insert. Here, we have keys and values. A hash table uses a hash function to compute an index into an array of buckets or slots from which the correct value can be found. The hash function will assign each key to a unique bucket, but this situation is rarely achievable in practice, and this is when collisions occur. So what is a collision? A different keys that are assigned by the hash function to the same bucket. This is a collision. In many situations, hash tables turn out to be more efficient than search trees. So we are just in theory, we are able to achieve the order 1 constant time complexity because the hash function, sometimes we are not able to build a perfect hash function. Maybe it's not exactly order 1, but it's very fast. So hash tables are used in caches, databases, sets, whatever. So that's the average time complexity for search, insertion, and deletion. It is order 1. Of course, the worst case is linear time complexity. So let me tell a few words just to summarize again the collisions. The collision resolution we can solve the collisions in two ways, chaining and open addressing. What is the chaining? We put multiple entries into the same slot with the help of a linked list. If there are many collisions, then the constant time complexity gets worse, of course. In the worst case, it is going to be linear because of the properties of the linked list. It has an additional memory because due to the references, of course, as we have discussed in the linked list section. Another way to solve collisions is the open addressing. It is a better solution, by the way. If collision occurs, we find an empty slot instead. And we can do it several ways. Linear probing, if a collision occurs, we try the next slot. If there is a collision too, we keep trying the next slot until we find an empty slot. That's what we were doing in the illustration section. The quadratic probing is we trying the slots 1, 2, 4, 8 units far away. So it is not the linear, we go step by step further away from the collision. If there is a collision again, we go twice as far away, then 4 as far away. And it's very important that I forget to mention that prime numbers are important in order to avoid clustering. A hash table or hash map is very efficient if there isn't any clusters at all in the hash tables. So for example, when we have 5 buckets, so 5 slots in an array, and the first 4 is full and the rest of us is empty, there's a cluster. So we should distribute our items as much as possible, and that's why prime numbers are helpful. Or the rehashing, it's a very out there are lots of algorithm relies heavily on rehashing. So we hash the result again in order to find an empty slot. So if there isn't a collision, we hash it again. If there is a collision again, we hash it again. It is a rehashing. So open addressing strategy requires that the hash function has additional properties. In addition to performing uniform distribution, it should also avoid clustering of hash values. Use prime numbers to avoid clustering, as I said earlier, and we have something that the load factor. It is the number of entries divided by the number of buckets. So the number of buckets is the m, where m denotes the size of the list, and the number of entries, of course, is the slots that are full. With the growth of the hash table's load factor, number of collisions increases, which leads to the decrease of overall table's performance. So the solution is to resize the table when its load factor exceeds given threshold. And remember that hash values depend on table size, hence hashes of entries are changed when resizing. An algorithm can just copy data from old storage to new one. It's very important. So that's why it's very expensive to resize a hash table. It's not like resizing an array. Okay, we just have to copy all the items. But here it is we are not able to copy the items. We have to do the hashing again. But resizing is done at once, and operation which triggers resizing takes ordo n, so linear time, to complete, where n is the number of entries in the table. This fact may make dynamic size hash tables inappropriate for real-time applications. When we want to insert lots of elements, then we want to get lots of elements, so we have to increase the size and decrease the size. If we want to resize lots of times, then it's not going to be efficient. So the applications, of course, we can use it for databases. Sometimes search trees, sometimes hashing is better. Ternary search trees are a bit faster than hashing because it's not relies heavily on the hash function. And as I said earlier, it's very hard to write a good and almost perfect hash function. If we want to count given word occurrence in a particular document, we should use a hash table. If we want to store the data and want to create or construct lookup tables, for example, if we want to check whether the passwords that the user entered was correct or not, we have to use hashing or hash tables, sorry. Lookup tables in huge networks, for example, lookup for IP addresses. There are millions and trillions of IP addresses, so it's a huge data. And if we approximately can use ordo 1 constant time complexity for looking up ID addresses, it's very good, very efficient. So that's why hash tables are very popular in networking. And the hashing techniques can be used for substring search. The technique of hashing is becoming more and more popular. Lots of cryptographic algorithms relies heavily on hashing. So that's all about hash tables. Thanks for watching.